This lecture is going to cover the next part of initial conditions of cloud collapse, of core collapse, and we're going to talk about the initial conditions of the unstable core. So, as we mentioned, stars form from gas in the interstellar medium. But we want to ask now, what size and mass scale of gas blobs will collapse under their own self-gravity? So how big are the things that form stars? What makes up the unit of star formation in the interstellar medium? So to determine that, we're going to look at the equations that govern things like this. This again is Barnard 68, a dark cloud where the darkness here is the gas and dust that's blocking out the background starlight. So the first quantity we're going to calculate is called the Jeans mass. This is a very commonly computed mass that's used in star formation. It sets the scale at which fragmentation occurs, and we'll talk about this word further. But it does not formally work out, meaning that the math that we use to calculate the Jeans mass is technically not self-consistent. So instead of using the formal derivative here, we're going to just walk through a back of the envelope approach you can use. When I say back of the envelope, I mean we're going to use very simplifying assumptions. When you go and do the homework, you're going to derive the Bonnor-Ebert mass, which is more self-consistent and takes into account an additional term that I'll talk about later in this lecture. Some good resources to look at for this are the Krumholtz textbook, chapter 6, which basically follows the same derivation and goes into a lot of detail, and Pala and Stoller, which is the 2004 star formation book, chapter 9, does the same derivation. So the Jeans mass and the Bonnor-Ebert mass are both critical masses, which means they are the mass at which outward thermal pressure exactly balances inward gravitational pressure. They are the most massive thing that can just barely balance with thermal pressure, the inward gravitational pressure. Anything more massive will collapse. The Jeans mass is something we calculate in an infinite uniform medium, and that's the reason we say it's not self-consistent. There is no infinite uniform medium. The Bonnor-Ebert mass instead considers the external pressure and is more realistic. But the Jeans mass is easier to calculate, as we'll show. So to give you a sort of intuitive meaning for the Jeans mass, we can say that a blob of gas, so any gas collection sitting out in space that is more massive than the Jeans mass, which means it has to have more mass in a particular volume than the Jeans mass, will start collapsing in on itself, and then it won't be able to stop. It will undergo free fall collapse after that point. So we're going to go through the derivation using essentially dimensional analysis. I'll say dimensional analysis means we're essentially matching two arguments that have the same units, two quantities that have the same units. So I'm going to start off by giving you the sound speed and the escape speed. So the sound speed is how fast the average particle moves in a gas, and that comes from thermal and statistical physics. And then the escape speed is how fast a particle has to move to escape from a gravitational well. So that one should come from gravitational mechanics. You may have computed the escape speed when you're trying to figure out how fast something has to go to escape Earth's gravity from the surface of Earth, for example. Well, the same thing can be applied to clouds. The how fast a particle has to move to escape the cloud's gravity. So the two values are C sub s is what we use for the sound speed, and that's the square root of kT over m. So the constants are all described below. K is Boltzmann's constant, T is the temperature in Kelvin, and m is the particle mass. The escape speed is the square root of gm over r, where g in this case is Newton's constant. M is now the mass of the cloud. So that's why we have capital M and lowercase m here. Mass of particle, mass of cloud. And r is the radius of the cloud, or the radius at which we're evaluating the escape speed. I note down here that the particle mass we're using, that's the mean particle mass, is often written as mu times the atomic mass unit. So mu is also called the reduced mass or the mean free particle mass. But it's the mass in atomic units. So mu is 2.37 at solar metallicity. To go from mu AMU to a mass in grams, you multiply by the atomic mass unit, which is 1 hydrogen mass, or that unit is also called 1 Dalton. We generally don't worry about the difference between a hydrogen mass and a proton mass. Those are the same to within the accuracy we'll care about. All right, so what we do is we then set these two quantities, the escape speed and the sound speed, equal. And that's saying that on average, particles will be bound to the cloud at this scale. So we just set those equal, square root of G capital M over R equals square root of KT over lowercase m. And we just solve for M, the mass of the cloud. That's simply square both sides, move R over G to the right, and we have M equals R over G times KT over M. Or if we want in terms of the sound speed, we just have M equals R C sub S squared over G. We want to get the gene's mass now in terms of the density of the medium instead of being in terms of the just the radius, because we are starting off with the assumption that we're examining a uniform density medium. So to do this, we're going to write out the definition of the density. So density is just mass per volume. And we're then going to write it as mass divided by R cubed. And when doing this, we're implicitly saying that we're looking at a cube volume, not a sphere, because then we would have 4/3 pi R cubed. But we're only doing sort of an order of magnitude estimate here. So those constants of order unity, meaning a bunch of constants that have that are about 1 plus or minus 1, we're just going to ignore for this context. This is correct if we're looking at a cube, though. So we take our definition, rho equals m over v, or m over r cubed. We solve for r because we have r in the equation. So r is just the cube root of m over rho. We then plug that into our equation for mass. So we have m equals r c sub s squared over g. That was one of our forms of m previously. Put r in there, and we get m equals the 1/3 over rho to the 1/3 c sub s squared over g. Now we have m on both sides, so we're just going to take this m over here to do a little rearranging. So we then have m to the 2/3 equals c sub s squared over g rho to the 1/3. We then take both sides to the 3/2 power, m equals c sub s cubed over g to 3/2 rho to the 1/2. And now if I write this out, I'm just calling our mass now as our gene's mass. And I put in the approximate here to remind you that we did a derivation where we made some specific assumptions about the geometry. We're going to call the approximate gene's mass this value. So we could also go and plug in the speed of sound into that equation to calculate the gene's mass as a function of temperature instead of as a function of the sound speed. So we do that, we're just plugging in c sub s equals square root of kt over m, and we had c sub s cubed here. That m is just coming from this equation. And then we reduce that down and drop the constants to say that the gene's mass is proportional to temperature to the 3/2 power divided by density to the 1/2 power, or square root of density, 1 over the square root of density, or temperature cubed square root. So any blob of gas that has a mass greater than the gene's mass is unstable to gravitational collapse. And what this equation tells us is that warmer blobs are more stable. So you have to have a bigger mass thing for it to collapse. and denser blobs are less stable. They're more prone to collapse. We're going to do one more calculation, which is to ask how big in the size, so linear size rather than mass, can one of these blobs of gas be stable? And this size is called the gene's length. So the gene's length is written as lambda sub j, and that can be obtained by just solving for r and calling r lambda j. So we just redefine lambda r and lambda j to be the same thing. And then we're using our equation for density, where r equals the cube root of m over rho. And then we're going to plug in our gene's mass here. And we get that the gene's length is then the sound speed divided by the square root of g rho. So we did an approximation here to get this equation for the gene's length. If you actually did the formal derivation out following the math all the way through, you would get this as the exact answer. And note that these are the same, they only differ by square root of pi. So we got a very accurate answer just by doing this dimensional analysis approach. Okay, so again, the gene's mass and gene's length define the largest mass and the largest size that will not undergo collapse. Anything bigger does collapse. The reason a larger length results in collapse is because a larger gene's length includes more mass in this uniform. And more mass means more gravity. So now we're going to go through some numerical calculations just to show what the size scale is. What is the typical gene's mass in a molecular cloud? So we ask, what is the gene's mass and what is the gene's length for a 10 Kelvin, 10 to the 4 particle per cubic centimeter cloud? And I've given you both the gene's mass and the gene's length here. I want you to pause the lecture at this point and go do this on your own. I've actually put a quiz up on Canvas, so you will have the opportunity to enter these answers in, and you can go look up the constants. I've given you some of the constants, but not all of them. I'm just going to pause for a second so you can pause here. Then I am going to go through and show you how I have calculated this. So I am going to do it using AstroPi's units tools. So this is Python code here, and I am doing from AstroPi import constants and from AstroPi import units as u. I'm going to be using this frequently throughout the class because it's a very convenient way to get units right. So I define the temperature to be 10 Kelvin. I define the sound speed to be Boltzmann's constant, K sub b, times the temperature in Kelvin, divided by 2.37 atomic mass units, or 2.37 Daltons. I define the density to be 2.37 Daltons times 10 to the 4 per centimeter cubed. So it's 10 to the 4 particles per cubic centimeter, but then I'm multiplying by the mass per particle. And then the gene's mass is just C sub s cubed divided by g to the 3/2 power divided by rho to the 1/2 power. And then I want to give that in solar masses. So I write this out, I run this calculation and do this conversion, and I get that it's about 1 solar mass. So the gene's mass is about a solar mass in a 10 Kelvin, 10 to the 4 particle per cubic centimeter cloud. The gene's length, we're going to use this equation, and this is part of the reason that I chose to do this in terms of sound speed. It made it very easy to do. It's just pi times the sound speed squared divided by g divided by rho. All of that is sitting under the square root, so it's the 1/2 power, and I convert that to parsecs, and the gene's length is about 0.2 parsecs. All right, so you're going to do some of those exercises just to make sure you know how to evaluate these equations. But part of the reason we were looking at this is because the Barnard-68 is actually quite close to this, close to 0.2 parsecs across, and it's close to solar mass. Not exactly, though. It's actually a little bit closer to something else that we're going to talk about. Right. The formal derivation of the gene's mass is covered in an ISM class, and you can also find that formal derivation in the Krumholtz textbook. One of the reasons you might want that formal derivation is that if you go through that math formally, you can derive the growth rate of the instability, but we're not going to do that. It is a little bit beyond the scope of this course. Okay, the Bonnor-Ebert sphere is the slightly more accurate model of blobs like Barnard-68. You're going to derive the properties of the critical Bonnor-Ebert sphere in homework. The Bonnor-Ebert sphere is the largest mass that can be thermally supported against the combination of gravitational pressure and external pressure. So the gene's mass was just balancing internal pressure against gravity. The Bonnor-Ebert mass is balancing against the internal pressure against gravity and some external pressure. So the way we do this is we start off with something called the Virial Theorem, which specifies the balance between different forms of energy. And I'm going to walk you through the equations, the basic equations that we're going to start with before we even get to the Bonnor-Ebert sphere. And this is you're not going to have to derive anything from these equations, but I want to make sure you've seen how they're done in at least one example. My caveat here is that if you try to follow the Krumholtz text, he uses tensor notation, which is something that I'm not even familiar with. I do not expect you to be. So I'm not going to follow the exact details of how he does the derivations. I'm just going to walk through sort of the physical meaning of the various terms and the way you're going to use them. So we start off with the equation of motion. So we're going to use the conservation of mass and conservation of momentum as the basis of the Virial theorem. And these together will make for the equations of motion, which, in other words, that tells you if you start off with some setup where gas is sitting in some location, it tells you how it's going to move over time. So this is a direct quote from Krumholtz. To derive the Virial theorem, we begin by imagining a cloud of gas enclosed by some fixed volume V. So you have a volume of gas, and it has some surface S. What we want to know is how the overall distribution of mass changes within the volume. So we first write down how the mass is distributed within that volume. And that is the moment of inertia. The moment of inertia is defined as the integral over some volume of the density times the radius squared. So that's the distance from the center squared. We then take the second derivative of the moment of inertia with respect to time. And this gives us the ability to get an equation for the time evolution of the density distribution. We have some blob of gas that has some density distribution. We want to know how that changes over time. In short, what's going to happen is the blob is going to collapse and the density in the center is going to go up. But we want to know how that happens. And basically, when does that become a star? So when we take that second derivative, we write the second derivative with respect to time as double dot there. And so the second derivative of the moment of inertia looks like this. And I'm going to then define what all these terms are. Here they all are thrown out on the screen. And I'm going to talk through these slide by slide, but this is your reference slide to come back to if you want to see how all of these terms are defined all in one place. So the first term is the thermal pressure. So this T, which math style T, is the volume integral. So we're integrating over the whole volume of the sphere of the rho v squared, which is the thermal pressure, plus P, which is the Rho v squared, I think, is actually the kinetic energy of bulk motion, and P is the thermal pressure. I've mixed these up. In any case, we have thermal pressure there, and we have a bulk velocity motion here. These are both things that support against gravity. Both thermal pressure and random motions in the gas both have some component that's pushing outward if they're isotropic, right? If the gas is moving in all directions, that's what isotropic means. It has some outward force that's pushing back against gravity. This is a volume integral because both the thermal and kinetic pressure are distributed throughout the volume. Okay, so that's our kinetic energy term. The next term is the confining pressure term. So we write this as T sub S because it's a surface pressure. So the S here is for surface. It's a surface integral. So R is the distance from the center to that surface. P is the pressure at that surface. We integrate over the surface. So this is basically how much somebody's pushing down on, or the external cloud is pushing down on the outside of our cloud. You can think of it as somebody grabbing a balloon, putting pressure on the outside. The somebody is the rest of the interstellar medium. So we're now going to make a simplifying assumption that there's no magnetic field, because that's just too complicated to deal with right now. And there's no gas flowing across this surface. So there's pressure, it's pushing on the surface of the cloud, but it's not flowing in. We also haven't talked about self-gravity. That's not part of this external pressure. Gravity, we are going to write separate. So as I said, the B term in that moment of inertia equation is magnetic, and we're going to ignore it. W is our gravitational term. So that's the binding energy of the cloud under its own self-gravity. And that's how much gravity is tugging the gas inward. It's trying to make the cloud collapse. So that's a volume integral of the density times our radius vector. And then this is times the gradient of the gravitational potential. So this term looks pretty complicated, and it's actually fairly complicated to evaluate. But for now, we're going to stick with just conceptually. And conceptually, it's not so hard. It's just asking how much pressure does the gravity internal to a given point exert on that point. Note that this is, again, a volume integral. So the gravity, if you have learned in classical mechanics, it's only the gravity internal to a point that's exerting force inward. So the stuff on the outer surface is feeling gravity from everything inside. The stuff toward the center actually doesn't feel any gravity, but it's already at the center. And everything in between feels some gravity, but and the amount goes more and more as it goes further out. Okay. In the homework, you're going to use this form for W, for the gravitational pressure term. And I hope this is somewhat familiar, that you should have seen this in classical mechanics. But basically, this W term is negative because it's pushing inward. There's some A here, which is just a constant. And as a constant, that's of order unity. In other words, in this case, it's 3/5 for a uniform cloud. And we're not going to worry about that number, basically. But if you want to learn more about that, here's the source you can go to. And then it's just Gm squared over R. Okay, so our full equation of motion coming back here is this. What we're going to do is look for the equilibrium case, right? The equilibrium case is where we start off with zero change in the moment of inertia, where it starts off stable. So in that case, we've already said B equals 0, so we're just ignoring that term. But then we're going to set I equal to 0 to find our equilibrium case. We end up with this, twice the kinetic energy, kinetic plus thermal energy, minus the surface pressure, plus W, which remember W is negative here, equals 0. So both T sub S, W are pushing inward, T is pushing outward. Then we're going to take one more simplifying assumption and say, well, if there's no surface pressure, then we can define something called the virial parameter. And I'm going to explain this one because this is commonly used in the astronomical literature, and I'm going to show you some measurements of this one. But the virial parameter is defined as so. It's written as alpha sub vir, also, this is an alpha. And it's twice the kinetic energy divided by the magnitude of the gravitational energy. So with this definition and this equation up here, we can see that if the virial parameter is greater than 1, that means the kinetic term is greater than the gravitational term, and the cloud is going to expand, so it won't form a star. If alpha vir is less than 1, it's going to contract or collapse, and then may form one or more stars, right? That's when gravity wins over the internal energy. I'm just going to toss out a little caution here that we just defined alpha virial to be this number, which means that the critical number, the one that divides expansion from contraction, is 1. But if you read astronomy papers, you will sometimes see people drop the 2 here, and then the critical number becomes 2 instead of 1. So just be aware of that when you're reading literature. You have to see how they define it in any given paper, because it's not, we don't stick to common definitions. The reason this is an interesting parameter, though, is that it's often used observationally to test whether a core is stable or not, which is kind of a coarse thing to do, but it's not bad. It's also often used in theory just as a starting point. You just decide how much energy you're going to start in a simulation versus how much gravity. So there's a problem. If we want to try to observe this, it's actually very hard to observe cores that have alpha that are far from 1. And the reason is that if you have a core that is just below 1, right, it's one that's going to gravitationally collapse, it suddenly just starts collapsing. Okay, great, it undergoes free fall collapse. But when it does that, that very gravitational collapse accelerates all the material. It means that you will then observe a velocity that is basically close to the equilibrium velocity. That material gets accelerated, so what we see looks like it's close to gravitational equilibrium, even if it's actually collapsing. This is a problem that makes observational astronomy somewhat challenging. Right, that, in other words, the measured virial parameter for collapsing core will be the same as that for a static core. So the alpha virial is only really a good stability measurement if we're looking at a static core, which we think we're probably not. The opposite case, if alpha vir is much greater than 1, that means that it's expanding, and we're just not very likely to see those clouds. Those are the ones that are blowing apart, so they don't live for very long either. I'm going to show you now some data from real observations, and there are 2 different observational data sets here. On the left one is from Kaufman et al. 2013. On the right is from Barnes et al. 2012. And the y-axis is the virial parameter alpha in units of, in a logarithmic scale. And in this case, their alpha equals 2 is their critical parameter. So this is one of the things I was cautioning about. People define different alphas. And they see things all clustering around 1, where there are a lot that are down low. There are lower virial parameters at high mass and higher virial parameters at low mass. Unfortunately, what they're pointing out is that there's this trend whenever you observe virial parameters that sort of means that we're probably not really measuring the right thing here. This is the sort of trend that you wouldn't really expect to occur based on the physics we understand. The Barnes observations over here sort of have the same, show a different observational problem, where these red points that are attached by a line are showing what happens if you calculate the virial mass by looking at one object versus subtracting off the background around it. And the point here is that depending on how you do the measurement, you get very different answers for whether something is unbound with a high virial parameter or bound with a low virial parameter. So this is really just highlighting some of the challenges we're facing. Well, it's part of why ISM and star formation study remain a very active topic of study, because these sorts of biases crop up all the time. Okay, so In the homework, you're going to use the Virial theorem as the starting point to derive the Bonnor-Ebert mass and derive some of its properties. The homework's going to walk you through some additional derivation steps. Right. So what we've been talking about are prestellar cores that are the things before stars form. And the Bonnor-Ebert sphere, or if you want, the gene sphere, is that the basis of the idea of this prestellar core. These are our units of star formation. They're the objects in the interstellar medium that, if we find them, they will collapse to individual. We know they'll collapse to individual stars. B68 is our prototype. And the surprising thing about this one is that it really matches well to this particular profile, which is the Bonnor-Ebert profile. So you're going to dig into that in the homework and show that this is the case in the homework. So I want to highlight some assumptions that we had to make along here and some things that we left as open questions. One is that we said the magnetic field was 0. Next is that we assume that there's no flow across the boundary, which means there's not additional material being poured in. We assume that there is kinetic energy pushing outward that is not caused by thermal pressure alone. We completely ignored rotation, which is going to be a very important topic as we move forward in the class. And we ignored any sort of asymmetry, right? We started with spherical symmetry. So all of these things are problems with the model we just developed. They're sort of problems with our spherical cow model, but it still works pretty well. So the magnetic field, I'll just say briefly, is an additional support term, meaning it fights against gravity, but the magnetic field is not isotropic. It also has the problem that the magnetic field doesn't couple very well to neutral gas. Most of when we're talking about molecular gas, it is neutral. So it can flow freely across magnetic field. It's only ionized gas with a charge on a particle is actually affected by the magnetic field. And the problem is that if the gas can freely flow, meaning it's not well ionized, that's referred to as ambipolar diffusion. And it means that the magnetic field doesn't do much. There's also the fact that even if the gas is fully coupled to the magnetic field, so even if the magnetic field works perfectly, collapse along the magnetic field lines is always just like the models we've done. So the effect of the B field is probably actually just to flatten out clouds because they can only collapse one way rather than to stop collapse. So magnetic field doesn't necessarily stop gravitational collapse. It just makes it happen differently. The flow across the boundary case, well, you can add that term back into the equation. And we'll just point out, without doing any of the math here, that if you add this term in, you're pouring more stuff in, that makes the sphere less stable. So the Bonnor-Ebert mass becomes smaller, or the gene's mass becomes smaller because you made it less stable. But then we have a problem that the mass we calculated is smaller than the final mass that's going to end up in the star, right? We're pouring more in, so we don't know what the final mass of the star is going to be. This is actually probably a pretty realistic model, but it's only been developed really in the last few years. And it's not yet part of this course. But I've given you some links here to some models, some simulation, some theory work and some simulation work from some theorists who have looked into how this might happen. Finally, I mentioned the kinetic energy term. We said part of the kinetic energy term is the energy of bulk motion. So it's not the motion of individual particles, but it's the motion of individual blobs of gas. So if that motion is truly random and isotropic, then it works as a supporting force. It behaves just like thermal pressure. And this argument is the one that underlies something called the turbulent core model, which I'm giving you the reference for here. But this argument is controversial. We don't actually know for sure that that kinetic energy actually is working as an outward force. It's possible that because we're basically calling it turbulence, and we don't, and if it is turbulence, it's supposed to decay very rapidly, meaning it goes away, it becomes a different form of energy very quickly. It might not work to hold up the cloud against collapse. So this remains another uncertainty, another unanswered question in star formation. And then, okay, I think I'm getting closer to finally. Rotation is a big deal. This is how we get to disks eventually. Rotation will support any object that has angular momentum, but just like the gravitational field, it only operates in two directions, not the third. So if you start off with a cloud that's rotating, it's still going to collapse. It's just going to collapse in perpendicular to the rotation and not in the other direction. So it's going to make a pancake or a sheet instead of a dot. But we still have a big question that we're going to talk about a lot more, which is how does the angular momentum get removed and what does it do to the system? Asymmetry in the initial conditions, so not spherical, not cubic, is the other key feature. And this is actually going to lead into another lecture. We're going to talk about the filamentary initial conditions of star formation. There's some historic discussion if you read the Paula and Stuller book, and I'm just going to give you the TLDR. You can read this yourself, but magnetic fields do support protostellar clouds against collapse. And if we follow the Jeans analysis, you would conclude that, and you include that not all clumps that we observe are undergoing gravitational global collapse, that there's some extra source of support. The last point I'm going to leave you with for real is that the magnetic field actually has been observationally pretty well ruled out as being an important supporting force by this particular review article, which this is sort of the key figure from it, but it basically said this blue line here shows how much, well, let me read the axis here. The x-axis is the density of the gas. The y-axis is the magnetic field strength. And the blue is showing the line where above it, the gas we're looking at would be supported by magnetic field. It would not collapse. Below it, the gas has enough gravitational energy that it's going to collapse, or at least it cannot be supported against collapse by the magnetic field. There could be other things that keep it up, but not magnetic field. And basically the conclusion is the magnetic field is never strong enough to support cores against collapse. So there does seem to now be reasonably broad evidence that giant molecular clouds are closer to undergoing free fall collapse than they are to being in gravitational equilibrium. So we still haven't successfully answered a now nearly 50-year-old question about why is the star formation rate so low? This answer is yet another open question, and we think that feedback plays a key role. That's something we'll revisit in the future, and this is now the end of the lecture.